Moin, my name is Carsten Becker, and I would like to kick off our presentation with a short countdown. No? Okay.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Okay, hello everyone. I'm Robert Böhme, and now I'm trying to push this button. And does it work? Nope. Okay.
It works.
Works? No, not. It works. Okay, it works. So let me introduce to you the part-time scientist team. For those of you that hadn't been there 12 months ago, and it's exactly 12 months ago, so we were like 365 days ago, we were here exactly in the same room at the very same place, and introduce to you our team and its mission to send a rover to the moon by 2013. So who are we? We are the first German team participating in the Google Lunar X Prize competition. So far we got to be the biggest European team. And we made it in the last 12 months, we made it that we were amongst the competition leading teams. So our team consists of by now up to 70 scientists, researchers and engineers working on sending a rover to the moon. So now I will hand over to Carsten, who will give you an overview of what we've done in the past 12 months.
Okay, so previously at the part-time scientist, I represent a short interactive overview of what we have done. Our team was funded in mid-June 2009, and we acquired several partners before we first got our press coverage at Financial Times Deutschland. And we acquired more partners while on the go. And we had one of our biggest presentations at the 26C3 last year, where we presented our first prototype, the R1 rover, which we are going to talk about a bit later. And we also created a Facebook community at that point, and we did what we could do best, acquire new partners, and worked very hard on our second generation rover, which we presented at the ILA, the International Berlin Air Show, and we presented it to the public there. We also had one of our first TV interviews, and our Facebook community grew up to 5,000 people. And our rover, we were tested on the sand beach at Hamburg, and I was very surprised to see it working, especially since there was some camera rolling and it would be shown on TV. And just this month, we presented our lander model, which we are using to land on the moon. And now we are here, and we are very happy to be here. And Robert is going to present you what we have done in 2009, the highlights.
2010.
Okay,
sorry. No problem. Okay, let's look at some highlights of 2010. So one of the things that we have is, as Carsten already mentioned, we went to the ILA Berlin Air Show. That is the biggest European air show that you have. So there is everything that's related to aerospace and flying around is represented there. And we had a booth there and showed our R2 rover, which is the R2A edition. And I will tell you more about our rover prototypes. The tiny little guy that's called R2B, it's already the upcoming, is standing over there. And we'll get to him later on. And one other thing that we have, and this is our first world premiere today, because I promised that we will have 2 world premieres. And the first one is that as of today, we entered into a partnership in a collaboration with the DLR. So most of you know the DLR as the German Aerospace Agency or as the Deutsche Zentrum für Luft- und Raumfahrt. And now we are at Future, we are going to work with them, and a little bit soon, Carsten will tell you some more details about it. And another big thing that we did in 2010 is that by mid-2010, we went into a partnership with the TU Hamburg-Harburg, and they're helping us with all the electronic parts. And we have a section for them later on too. Okay, now let's come to my favorite topic. Let's talk about rovers. So our most recent rover prototype we have is called Asimov Junior R2B. So we're having like multiple series, we are always numbered upwards. So we have the R1 rover that we showed you last year, and we talked about building another one. And this is actually the second release of our second series, so that's why it's the R2B. And what you can see over there, let me try to point it out. What you can see is that we have two stereoscopic cameras. So what do you use them for? You use them for 3D imagery. So you take two pictures and you can overlay it and you get the 3D picture. It's not just intended to show it at the nearest IMAX that you have, it's a 3D movie. It's more or less intended to see if there is a hole in front of you. So you can make the rover aware of its surroundings. And this one is quite spectacular. This is a so-called telelens. The telelens itself isn't spectacular, but try to build a telelens that is working in vacuum and by plus 100 degrees or minus 100 degrees. So we'll talk about the lenses a little bit later. Okay, and one thing that is very specific about this rover is that it has 28 brushless drives that control all of its motions. So we have at least, for example, one drive here for the direction. And building brushless drives, I don't think that we talked about. We spent a lot of time figuring out how to build drives that can work on the moon. So you have vacuum, you have plus 100 degrees Celsius, you have more than minus 100 degrees at night. And that's why we're working, for example, with two companies that help us building these brushless drives. Another topic about brushless drive is that the electronics behind it is quite complicated to control them because you really have no feedback about it. You can't easily tell where this wheel is turning without having a way, and a self-invented way, to measure it. So, for example, if you set the rover onto the ground and you have no defined way of knowing how the wheels stand, then you have a little bit of a problem in software ways. Because there's nobody there that tells you that the wheels are standing in a completely opposite direction. Okay, and what you can see on the design is a little bit possible to see it right here, is that we've designed the R2 rover especially to dissipate all the heat. Because if you're thinking about 100 degrees Celsius and vacuum, you're having a problem. There's nothing that carries away the heat that you have in all the components. So, and even if you have an environment temperature of 100 degrees, it always adds up the temperature that you have for the electronic part. So we have to get rid of this heat as best as possible, and that is why we've chosen this basic design approach. We can tell you a little bit more about the heat dissipation afterwards, because it's quite a complex topic. But this is one of the key reasons why we changed the design between Asimov R1 and R2. Speaking of, the Asimov R1 rover, which we showed at the last year, this is just the wheels of it, we used it for almost 4 months to test drive all the electronics that we have and the brushless drives. And then, as I said, in less than 4 months, we were able to jump to our second generation rover prototype, which is what I think is really quick. And I think this is something that really speaks for the team, is that we're always trying to do really fast development. And now, we come to the second world premiere today.
Yeah, today we are really excited to show you our latest rover. We have the problem of building rovers that can be used for software development, and so what we came up with is really brilliant. I will just show you a video and then you will see why we are so excited about it. Okay, I'm kidding a little bit. This is not the actual rover that we designed, but it is based on it. The wheels are actually from it, and I will show you what we have done to make a rover that is cheaper than the R2 and still has all the features that we need for developing software. So the idea is we have a development team that is spread around the world, and actually it would be very useful if we could ship an R2 rover to every single software developer so that they can develop their software using the real hardware. The problem is the R2 isn't cheap. It's like 10K plus, and so we don't have like 10 of them or so. But the R0 edition that we developed is less expensive, and every software developer can easily have one of those. on their desk. And we made that possible by using standard servo components as for steering and standard servo components for driving. And we developed a PCB that is capable of driving all those servos so that we can offload all the CPU power that we need to the BeagleBoard, from the BeagleBoard that we are using for software development. So why are we using the BeagleBoard? And the reason is quite simple. It has a very capable OMAP processor on it, which is a rough equivalent of the PowerPC that we are going to use in the real rover, and we are using it on the R2 rover already. And it also happens to be able to run QNX, which is our operating system of the choice that we are going to use. It is also quite similar to the R2 in that it has a tiltable solar panel, and as I said, is made of cheap components. And I got a little surprise for you. So if you like to have some piece of rocket science on your desk, you will be able to get your hand on this hardware if you want to. We set up an email address, and if you want to have one of those, you can just email to r0@parttimescientist.com, and we will be able to give you the metal parts, the wheels, and the PCB that we have for it. And so you can build one of those on your own. There is also a workshop if you want to test drive one of those later this day. You can go to room A003, and we will start the workshop at 8 p.m. And there you can put your hands on this thing, and even the Mate box, if you want to drive around with the Mate box. It's always fun. But we didn't just develop rovers, we did even more. We developed our first lander, and I will hand over to Robert to explain it.
Thank you. Okay, about powering up one cluster and getting in somewhere, you have to do a lot of trajectory calculations. And this is what, I think I mentioned it last year, we had an interview with Jack Crenshaw. He's the team leader of our trajectory calculations group, and he did the same thing back in the 60s, where he worked on the Apollo program. So, and he talked a little bit about that, how, I think really everything what we're doing, it tends to be immensely complex and impossible to do, but as he said, that he thinks that trajectory parts are one of the most complicated issues. So, the secondary most important thing about the lander is the payload itself. So when I'm saying payload, I'm referring to boxes like these. So for example, this box, that is a component, it's a payload box that could contain this rover over there. So the Asimov rover itself is designed to be in a compact mode. So for transportation, it's not it's like it's over there. It's not an extended. So after the lander has landed, the box will be unloaded, and I will see it on the next slide. And we have, theoretically, we could use like 4 of these boxes, but in practice, it's a little bit more like that all space is already reserved, and we need at least one of the boxes, for example, for the electronic parts. So in fact, we will end up with a little bit scientific equipment and one rover payload box. The other most important thing about the lunar lander is that you need the fuel tanks. That's quite obvious too. And in our case, we have 4 fuel tanks, 4 main fuel tanks. There are also several other ones that are a little bit smaller. They are for the guidance and control thrusters. These are just the main fuel tanks. The exterior side that you can see on the lander itself will be covered as best as possible in solar panels. And when I'm talking solar panels, I'm always referring to our special way of solar panels. And we showed to you last year the idea of developing a so-called, let me try to spell it, phased array integrated solar panel antenna. It's a pretty long word, and I have to find an abbreviation for it. And this is the basic idea behind it, is to combine a solar panel with an antenna. Because the solar panel and the antenna are always using the most space that you can have on a front, and that is a good reason why we want to combine them. One thing I think I missed it on the R2 release is that the R2 rover over there already has an early prototype of this technology that we presented last year. Last year we just talked about the idea of having such a solar panel, and this year we're just showing to you that we built the first prototype. So in general, if the lander is in a so-called landed position, it looks pretty much like this. So you can see that it's standing on its ports. And here we have the main engine, and we have, for example, the payload box unloaded with still the rover in a compacted mode. What you can see there is the lander where we showed it at the Euromode conference. There we had this world premiere for the lander just in December. And yeah, it's a 1:10 scale module. So why is the reason that we are building a 1:10 scale module and not the 1:1 module? It's simply as this, that the 1:1 version wouldn't fit in any laboratory that we have. And there is no need for it, because currently there's no need to build, for example, out of a rapid prototyping material a 1:1 version, because what do I want to do with it? The engines that are equipped on the lander only work in vacuum, so there is no way to ever let it fly around in your garden. So that is why we've decided to build smaller versions to do all the testing here on Earth in our laboratories. Yeah, okay, and this is just the so-called R0 version, so it's our basic design and test version. So we're looking at it and seeing, oh my god, we had a design error over there, and then we're trying to fix it. Okay, so now I'm handing back over to Carsten, and he will talk you a little bit about the electronic parts.
So one of the key challenges if you want to make electronic work in space is that you have so much that you have to take care of. For example, there is not just a temperature range from plus 120 degrees to minus 180 degrees, but there is also radiation, and radiation is doing awful stuff to your electronics, like flipping bits or doing even nastier stuff. So what we tried to accomplish is to concentrate as much hardware on one point as possible for adding shielding and to dissipate the heat. The problem is because you're in vacuum, you're perfectly isolated from the environment, and you need to find a good way to get rid of the heat that you're producing with your electricity, with your electronics. And so we focused on using Virtex 5 FPGAs, which have a nice PowerPC on them. And so we can use the PowerPC to run our operating system. In this case, we are using QNX. And the reason we are using QNX, for example, is that with Linux, we had the problem of developing drivers. We have almost no standard hardware, and we need to develop a lot of drivers. And if you're using QNX, you just write an application style. You can do all the user space I/O from, and all the interrupt handling from an application. And you also have some nice features like message passing, and it's smaller than, for example, the Linux kernel. And another nice thing is it has built-in watchdogs, so that you can say, well, if this application crashes, it automatically restarts, for example. Another nice thing about using an FPGA is that if you figure out, for example, JPEG 2000 encoding is really hard to do in a small PowerPC, then you can use an IP core, which allows you to offload the computational intensive part to the FPGA fabric. And what we have done in the past, in this year actually, is that we have developed IP cores to, for example, communicate with 1 gigabit per second between multiple FPGAs. We have an IP core that is taking care of the bits that are flipping from the radiation. We also developed the IP cores that are capable of offloading the computational intensive part of driving a motor. And the other thing that we are using is a JPEG 2000 video codec, and I will talk a bit about that in depth. In the last presentation, we just said that we want to transmit HD video back to Earth, and it should be stereoscopic, and this is quite a tough task to do. And so we looked at the options that we have. One of the obvious options is H.264, but the problem is that H.264 is that it's computationally very intensive, and we just don't have the power budget to do that. So we need to make sure that what we are doing is feasible with the power we actually have. Another thing with H.264 is that if you miss a bit or it's flipped or whatever, then the frame, the sequence of images will be broken for at least some frames. So we looked at JPEG. JPEG is a full frame format, and the problem is it just doesn't have the compression ratio that H.264 or JPEG 2000 has. And so we settled with JPEG 2000. There's also an IC available that we can use for offloading the encoding from the Power PC. So this is the video coding, and on the bottom layer of that is DVB-S2 stream. And if you happen to have a 10-meter plus dish in your backyard, yeah, I know, all of you have those, you can receive our video stream from the moon at a ham radio frequency of 10 gigahertz. So we really want you to be able to receive the data signals from the moon on your own, and that you can put it up to YouTube or do whatever you want with it. But we didn't stop with developing IP cores or software. We also developed new hardware. And what you can see here is our latest motor driver PCB, which is capable of driving in more complex terrain than the current one that we have. We also while we are developing the current Earth version, we are also developing the space version simultaneously. So for example, I said the radiation stuff is very awful, and so we need to make sure that the motor driver that we are using is also capable of working in space. And so we are simultaneously working on developing radiation-hardened motor drivers. Another thing that we are working on is a JTAG 2000 PCB and a solar panel charging, so that we can actually use the solar panel on Earth to charge our batteries. And most of that is done as part of our STEM initiative. So we're involving students whenever we can. But the idea here is that we use the momentum that we have to get pupils to think that being an engineer is something really cool. And so, for example, we are involved in the Moonbot competition, which is a Google Lunar X prize, but just done in Lego. And it's really cool and it's fun, and there have been many teams that participated, and we supported them by doing that. There is also the first Lego League that we are going to support, where you have to tackle very challenging tasks in Lego. And I was wondering if some of the students, of the high grad students that I have, are able to compete with the children I have seen there. Yeah, but students are very capable as well. So what you can see here is the first batch of our students that we experimented with. We call this problem-based learning, and we give them a task, and they are set to design things that we are going actually to use on the rover. And this year we stepped up the game a bit, and we threw in free pizza on Saturday nights, and the result is a Mate box that can drive around. And I think that's pretty awesome what we can do here. So, to get to the moon, we need a carrier that will get us to the moon, and Robert is going to talk about that.
Okay. Just before talking about the carrier, I just noticed one thing. I think I was a little bit too nervous in the beginning of the presentation, so I missed out to point out some things. And just one thing to be sure, as the name suggests, part-time scientist, it really is that most of the people who are working on this project, working on it part-time. There are some of them that can do this in their work time, but most of them, really is a motivational project, and it's about to prove a point to send a rover to the moon. Okay, so how to get it to the moon? As Carsten already said, you need a carrier. Okay, carrier to what? Because, as I said, our lander is going to send the rover from let's have a look, low Earth orbit to a moon. So what actually the carrier is for to get you from ground to low Earth orbit. Low Earth orbit is the area where most of the commercial satellites reside. It's pretty much near it. It's 150 kilometers above ground. And yeah, from there on, up to this point, it's not in our hands. But beginning from the low Earth orbit, it's all about our lander trying to get us from the Earth to the so-called low moon orbit. So what the lander is basically about to do is doing a lot of so-called burn cycles. So it's cycling its way, and it's entering a so-called translunar trajectory, and it's entering the low moon orbit. Low moon orbit is basically an orbit around the lunar surface. So this even isn't the most complicated part. Even while you're traveling 400,000 kilometers, it may sound complicated, but it isn't. Okay, it is. But it's not so complicated as the next thing I'm going to show you. The most complicated thing is to actually landing on the surface. I think this is, in my perspective, really the most complicated part. First you have to figure out, okay, where do I land? It would be good to land something like there. It should be there, that's a good point. But the problem is that even the most detailed map that we have on the lunar surface, and recently we got pretty good ones from the, I forgot the name, Alcross mission, that had took some pictures while rotating around the moon. And even this map can have, still has a resolution that can contain gaps, and these gaps are the size of our rover. So if I say, okay, we have a map and drive from this point to this point, then we can even have a big hole and the rover is driving right into it. So that is why we are going to use the Apollo landing sites as our landing sites. We want to use right beside the places where the Apollo missions landed. And what you can see is that there is a lot of imagery material available covering the whole area where these missions landed. So the good thing is that you can tell there is no big hole where the rover could fall into, and there's a flat surface where the lander can safely land. Okay, as I already said, we're just doing this for fun, and we want to send a rover to the moon. And that's almost all, except for one thing, that we're participating in the Google Lunar X Prize. And the Google Lunar X Prize itself is a competition, as the name suggests, set out by Google, which awards $30 million to the first team being able to do what exactly? Let's have a look what they have to do to win these $30 million. You have to send a rover to the moon, basically. So this already sounds familiar. Then you have to do something like a so-called soft landing. So what is the soft landing? Can't you simply turn off your engine and fall down and everything is fine? It's a little bit complicated because if you don't have a soft landing, the only other thing that you can have is a deep impact, and there's nothing. And there's nothing that will remain functional. So a soft landing means that your lander touches down in a way that all the electronics and hardware parts remain operational. So it meaning on a flat surface that all the landing pods behave correctly and that the rover can embark safely. So a soft landing is really the most difficult thing. Because in our case, a soft landing for our lander, in practical terms, if you translate it to Earth gravitational forces, it means a free fall out of 3-meter height. So just take this lander, take it 3-meter height, and let it fall. And it has to survive this fall with all its components, with all its payloads. And that's quite complicated to do, because normally you would have something that breaks. Okay, so once the soft landing is being handled, what is to do? Rove around the surface of the moon and travel 500 meters. That sounds okay. And what else is to do? We have to take images and video material in HD, 720p, and transmit it back to Earth. That's fine too. So why not? If you're there anyway, why not take pictures? So this is, if you do all these 4 things, you will get $20 million. So as I said, $30 million. There are some so-called bonus prizes. So you can get the rest of the 10 millions if you do some of the bonus prizes. And we aim for the following bonus prizes. We want to have our rover drive around 5,000 meters instead of 500 meters. In fact, all the components that we build are always built with so-called minimum requirements. I'm saying this specifically because I know a lot of teams that are competing are building it with maximum requirements. So speaking of building a rover that drives 500 meters and falls apart immediately, because there's no use for it traveling any further. So we are always building it to travel at minimum more than 5,000 meters. So there's another thing, it's called surviving the lunar night. The lunar night is a little bit more than 14 days of, what was it, minus 100?
Minus 182 plus 120 degrees.
Thanks. So it's quite tough to survive such temperature shifts. And I don't know, I can't say if it will work, but we will try to do as best as possible to get our electronics ready for it. Most of the mechanical parts are ready for it, because the final prototypes, and we'll talk about the mechanical parts on it later, but they should be already withstand it. But the electronics can be quite problematic at this. And what was the other part? The other thing was taking a picture of an Apollo landing site. And as we want to land there anyway, why not take a picture and get 5 million for it? So, and there's one thing, as you know, we've been here 12 months ago, so we competition 18 months ago, so it's 1.5 years. So by then, the competition is going on for almost 3 years by now. We have like 23 teams participating in it, And yeah, how should I put it best? This is a so-called GLXP scorecard. So there is an independent journalist who is looking at all teams and is ranking them and is putting them in perspective. And in less than 12 months, we've been going from a little bit from nowhere to be among the leading teams in the competition, which is really cool. So. Okay, okay, no, it's my topic, yeah. Just was thinking about, so how is it possible to, not just how is this possible, but most of this is a little bit possible due to the help of our partners that we have. And I was just going to give you an overview, and it should start. Yeah, now it is. Almost? No, yet. Yeah, there it is. So this is a little bit like an incomplete list of all our partners that we have, because all of them wouldn't fit on this page. So if you want to see all partners, you have to go on our homepage. And I just sorted out some of the most obvious ones, because we're always saying we have a partner in this field. And yeah, for example, just look at the list and we'll see, for example, they have a company like Crosslink Fibertech, who is specialized in making carbon fiber parts. So these guys are helping us in making the carbon fiber parts for the flight-ready models. So it's always pretty obvious. One new addition, which is just here and is being presented for the first time today, is Altium. So we have Altium as our new partner, and I think you already said something about it, huh?
No, I forgot.
Oh, you forgot.
We're using it to designing the new, very complex PCBs that we have, and the 3D image that you saw from it is actually one of the renderings that you can make with the software. The reason why 3D, for example, is important is that we need to pack up all the space, the electronics, into a very tight space, and we need to figure out how to get the heat away from this space. And so we're using Altium, which is a very capable software for exactly doing that. But we also have some new partners, some collaborations along the way. And for example, we visited the DLR, and they have awesome robots. This is Justin, and it's a robot that can shake hands and is supposed to be used on the ISS for maintenance stuff, for example. And they even have some humor. They're saying, "Caution, this machine has no brain. Use your own." So I really welcome that, because I don't want to have robot overlords. And yeah, so we have some new collaborations. And as Robert said, it's the DLR. And the reason we have the DLR is because they have so much experience in designing robots, be it small one, big one, tiny ones, awesome ones. They know they can do them all, and I have seen them on my own, and they are really astonishing. And so they even know how to make them run in space. So if we design our rover and we have some technical issue that we want to have a look at, then we go to the DLR and they are verifying of what we are doing. And we are in technology exchange of what we are doing. Another collaboration that we are entered is with the TU HH. And, sorry, TU Hamburg. So, and we are developing most of the electronics there, but we are also using the TU Hamburg to reach out for the pupils and high schoolers and to encourage them to do something useful, like becoming an engineer or a hacker, for that matter. And another collaboration that we now have is with the TU Berlin, which is helping us to choose just the right landing spot, so that if we see the first pictures from the lunar surface, it should not be a big rock blocking our way. And they are going to help us with that. And this is really a topic on their own. And now Robert is giving us an overview of two partners.
Yeah, we just selected two partners because I think it's fair to talk about at least two of them in more detail. We could talk about all of the partners, but I didn't want to put the entire presentation in it. And it's not an advertising campaign. Anyway, so one partner that I want to speak about is Schneider Kreuznach. So you may know them because they were the ones who provided the optics for the Apollo program. So they're helping us building the optics that we have in our Asimov rover over there. So as I said earlier, we have the stereoscopic lenses and we have the telelens. And as I said before, building a telelens that is working in vacuum is really a complicated task, and this is what they are doing for us. So yeah, all the optics will be provided by them. So they're yet again on the moon. And the second partner is something that most of the people already figured, but we never really announced it, is one-on-one prototyping. That is the company, as you can see, we can see it afterwards. We're having a lot of prototypes, and we always like to work with prototypes a lot, because we're having so-called agile development. Agile project development means that we're always jumping from the design phase to the production phase, back to the design phase, and so on. So we're doing a lot of testing and validating what we've done in our designs. This is quite important, and it's not often done being in the industry today. In the industry, you always have, for example, specifically in the aerospace industry, you always have a very long time where you're just defining one thing, starting to build it, notice that it won't work because you've overseen one tiny thing and step 3 years back in time. So, and they already invested a lot of money. So we use this rapid prototyping to instantly get prototypes to play with, that's one reason, but also to cut down the cost that we have. So yes, and these prototypes are being provided by one-on-one, and the greatest thing about them is, if I have, for example, on Wednesday, I sit there and have my rover in my CHD software and say, okay, I just want to see this thing drive or climb up that hill. Then I can send them all the files by Wednesday and get my working prototype on Friday, which is pretty cool, so I can play with it on the weekend. So I think, and this is a topic for you.
Yeah, so in the last year we have been also very active in the media. For example, we have been covered in several newspapers, we have been on radio, and we have been on TV on several occasions even. And this is one of our initiatives that we are trying to communicate of what we are doing so that you can see what we are doing, and we have several channels for that. For example, on our blog we are giving background articles on what we are doing and why we are doing that actually, so that you can read in depth why our wheels, for example, look exactly the way they look now. And we also have a growing Facebook community, which I welcome you to join. And there we are communicating in a more on a day-by-day basis on what we are doing, and we're giving short teasers of what is coming up, for example. And if you're really up to real time, you want to join us on Twitter, which is where we post all the news that we have. That, for example, we are standing at the CCC. Did you?
Yeah,
okay. And one of the biggest impact we had this year was, for example, by being on Spiegel Online. It's a very nice article and very well made, so you might want to read that one. But the question is, why am I talking about media if this is a CCC? Why am I not talking about how QNX message passing helps us to avoid deadlock situations between process intercommunication, for example? And the reason is very simple. The CCC is about the creative use of technology, and this is exactly what we are doing. We are using nowadays technology to build something that we can send to the moon, and if we would reach the moon and be there and no one would care, then our mission would be failed, even if we would get some millions. The thing is, we really wanted people to know that you can do awesome stuff as a scientist, as an engineer, or as a hacker. And so being in the media helps us to recruit the new hackers for the 28C3. And what we're planning in the future is what Robert is going to talk about.
Yeah, now we're almost at my most favorite topic. So talking about the future, let's have a look into the orb what the future will hold for 2011. So, future, there it is, and one thing that we have is we will going to do a lot of testing with testing and testing. So the next year is all about testing the prototypes that we already have, and testing is really the motto that we have for this. Because you can't do, as I already put it, we're doing agile development, so it really is a vital thing to always have your rover driving around and saying, oh my God, it can't climb up that hill, but my paper says it should climb up that hill, why isn't it driving up that hill? And trust me, we had such situations a lot in the last time. And once you've overcome the step that you always have this consequent testing, you can see that it's a lot of fun and it's quite important. So testing means itself that we will have more rover prototypes. In our case, as I said, we have the R2B edition right now. We want to build several more of the R2 versions, which cost way much into the 10,000s of euros. So it's not easy to say, oh yeah, I want an R2 rover. It's not that very easy Christmas present you get. And this is the reason why, by the way, for the R0 series. And the R0 series is another thing that we have for the future. We want every one of you and most of our team to work and start working with the R0 rover as soon as possible to learn more about the software development behind it. Because, as Carsten already said a lot about it. Another one thing that's very important is we want to have more lander prototypes. Because, as I said, the lander currently is the so-called R0 edition. As R0 in our terms means it's a basic design study. So we are looking at the design and saying, okay, there are certain aspects that need to be changed, certain dimensions. The most important thing in everything we're doing is dimensions. So you can't easily, for example, the weight and the size of it. So what we want to do next year is to build at least an R1 release of the lander. And of course, we will try to build it in a full-scale version, which is not as easy as I said before, because an R1 in a full-scale version would mean that you need to have the right laboratories. Because you're having a lander that is standing beside you with 3 meters height, it's a problem for most of the basements that you have. And one thing is, there it is. One thing is that we want to do, or we're already doing, a little bit more of media work, because we want to spread out the word as best as possible of what we can do as a part-time scientist. So one thing I want to point out specifically is we've already produced a lot of media material this year that it's going to be airing next year. So there's a pretty cool news coverage coming up from Servus TV, and it's going to air at 30th of this month at 6 p.m. on Servus TV. And I think you can even receive them free in HD television. But correct me if I'm wrong, but I think it's so. At least I can watch it for free. So yeah, and anyway, and we've already done several other interviews, and so the January and February we will get a little bit more insight. To note one thing about this one, for example, is that you can see how we created the lander. You can see how we designed it, how we built it. You will get a little bit more insight on the rover development itself. And of course, you will learn more about the team and the people behind it. Okay, so we almost at the end of the line, and I want to start the last phase of the presentation with the last short clip that we have.
I think it's obvious to see how much fun we are having building this robot, this rover, especially. But it took like 7 days to figure out how each part goes where, because we don't have a manual to build it.
There's no one to write a manual. Okay, just one thing. Before I open up the question and answer round, I want to say, if you're interested and want to join our team, or you think, okay, I want to participate or I want to help you, then we have a contact formula on our homepage. So just go to parttimescientist.com or mail to contact@pts.com. And I have to say one thing. At the last CCC Congress, we got over 300 inquiries in less than 2 days, and it took us like 2 months to even reply to the first of them, and I'm quite sorry for this. And I promise we will be better this time.
Oh no, don't promise.
I have this before. Okay, so now let's start the question and answer round.
So we have here the first question from the internet.
The internet, cool.
Okay.
Anonymous wants to know what kind of hard drives you're using in your moon rover and whether it's SSDs.
We are going to use flash-based system, not really like a hard drive, especially not the ones with the spinning disks. Those would be awful. But we have to use flash components, and we have to use ECC to make sure that all the bits that we are reading from it are actually correct because of the radiation issue, which also affects the flash storage. And we have to correct those incorrect bits by using ECC. So this is something very special to build.
And everyone else who has questions, please align at the microphones in the ways.
Hey guys, that's absolutely amazing and quite complex at the same time. So I'm going to ask you, like,
Thanks.
Out of the whole chunk, what's the really hardest thing you've encountered and what's the easiest thing? So if you could just solidify in 2 points.
I guess what is the hardest thing to do is a very easy question to answer because you go to every team and every sub-team that we have, for example, electronic teams, and they say, oh, the electronics are awful. Then you go to the trajectory team and they will say, oh, the trajectory stuff is awful. And then they go to the lender team and they will say, oh, the lender is the hardest thing to do. So there is really no easiest thing to do. Everything is really just complex and difficult to do. But if you have the right people and they are motivated enough, then you can solve those things. And we're very good at solving those things.
And I have to say, it's rocket science.
Yeah, it's definitely rocket science, and we are doing it, and it's fun.
Do you have any kind of method to test the radiation here on Earth?
Yes,
Yeah.
we have.
Yeah, we've always already gotten several offers, for example, from laboratories to use it. To put it as simple as this, yes, we have the possibility to test it, and yes, it's something we do, but not with the current, for example, PCB generations. This R2, I don't think I explained it correctly. We have this R revision scheme, and for example, if I say the rover is an R2 release, then I'm saying it's used for almost testing everything that the rover should do, finally. Then we are going to build a so-called revision tree, and the revision tree is consisting out of the final materials. This is very important because these are the only materials I can do radiation testing on. I don't have to put this rover into an oven and bake it with 100 degrees because I know what would happen.
Yeah, so basically the current hardware we are using would fail horribly if we put it into radiation. That's sure.
Yeah, my question is nearly the same. I would have asked what ways you have to simulate the radiation, and you mentioned that there are worse things than bits flipping. I would ask what you meant by that.
This goes. The worst thing that is happening is the total ionizing dose. So, for example, because we are using semiconductors, there are parts of the that are positive dotted and parts that are negative dotted. And if the ions are hammering all the time into this electrical charged parts, then they wear off, kind of. And so after like 100 kilorad, for example, some parts fail. But this is something that we do not care about too much. In last year we thought, oh my god, this is awful, but we figured out, no, it's not. Actually the total ionization dose is not as bad as we expected it to be in the beginning. Because the worst thing that we are having is the Van Allen belt, and on the moon we just have the 100 times of the radiation on Earth. And we can simulate single event upset, as those bit flips are called, for example, in our FPGA with the IP core that we are using. It's just a mode where you say, I want to have simulated bit errors, for example.
We have another question from the internet, and it is, how does the heat dissipation from the rover work in detail?
What?
The heat dissipation.
Oh, okay, that's complicated. I would have to explain it. Yeah, it's rocket science again, yeah. But I think I would just put it best to explain it after the presentation, but it's always complicated with the internet. And I think it's anonymous again. But anyway, I don't know if I have the slide ready.
One of the key components we are using for dissipating the heat is to actively transfer it to a region where we can actually dissipate it. Because we can't dissipate it in the direction of the sun or the illuminated part, but we have to dissipate it into the dark of the space, for example. And so we are using a mechanism to transfer the heat from one point to where we can dissipate it.
Yep.
This is a short and easy answer.
Hello. Talking about future, do you have any plans how to spend money that you are going to win?
Definitely. That's a good point, but most definitely not, because one thing that we are not doing is working with the prize money in any way. Our thing is it's not about winning 30 million US dollars, definitely not. For us, the motivation is to get this rover on the moon, and we would even do it if, for example, another team wins this competition, which is not unlikely because other teams get support, for example, from entities like the US military or NASA. So they have a little bit like an advantage, but we're doing our best to keep up.
Michael was proposing something like buying a big bathtub and filling it with money and then sitting in there. And I think that's quite a good idea.
Yeah, my question was pretty much the same, but I was just asking, how are you going to split up the money between the members of your group?
What? Okay. So we developed an algorithm kind of where the people that are working most on it are getting some part of it, but the problem is we are not getting the 30 million and split it evenly between the 70 people. The problem is there are some partners that want to get some of the money back that they are spending with us. So we don't have the 30 million to spend with. And, you know, I totally wouldn't count on winning this money. It's not like that we set up a rocket and then we are done. It's really the problem that it could explode on the launch pad, and this isn't our fault. And so he's already looking a bit angry. So
not yet. We have at least 5 minutes. So one thing, the financing is always, I don't think it's the most interesting topic, but it's always a topic where you get a lot of questions. So as I always put it, we are not using the prize money, which means that when this rocket is going to launch and it's containing our payloads, all our bills are being paid. That is the general idea behind it. So it's not like, and I have to put it like 10 times, because every other team that I'm aware of is going like, oh, we have 50 million of mission costs, and they are already subtraction that they are winning 30 million US dollars, which is pretty much wrong. You can't do such calculations, and this is one of the reasons why you ended up being bankrupt. So.
Okay, next question from the internet is whether you have any plans to take on other challenges like the X Prize, like those offered by the NASA or the DARPA.
Yeah. I know that this is a little bit complicated. I would love to, for example, join in on some of this competition. We already thought about it because there was something like the NGLLC, which is the Northrop Lunar Lander Challenge, to build a lunar lander which just works on Earth, starts at one point, drives to the other point, and lands there. And you can, I don't know what you could win, but I think it was some millions, but I don't know the number. So, and one of the things that we saw with these competitions that look like, hey, they could be useful for a moon mission, they're most definitely not. For example, the NGLCC, you build a lander that is starting at one point, flying to another point and landing over there. That's of no use, because the fuel that you have to use on Earth, the engines that you have to use on Earth, and to build a lander that has to navigate around the wind. So that makes totally no sense. So the lander would be 100% completely different from a lander that you have to build for a moon. And we already have enough to do with building a lander that works on the moon. So that is why we said we keep focusing on one competition.
Yeah, we are the part-time scientists, and we don't work full-time, at least not all of us, and we are already pretty busy sending a rover to the moon.
Yeah, I have a question concerning the lander. I was asking myself, how do you get around with the problem of carrying the fuel? I imagine you cannot just select a trajectory to the moon that brings you in a straight line, because that would be much too expensive. How do you manage that?
The straight line wouldn't even be the most effective one. There's a lot of things that you have to take in mind when you're working out the trajectories. So basically it can be said that we are taking the long way to the moon. So for example, the Apollo mission took like, I think it was 7 days, and we will, or 5 to 7 days, and we will have like 7 to 10 days of flight time. And it's also designed to consume less as fuel as possible. And in our recent calculations, we have quite good reserves. So these reserves is not something that you can bargain, for example, to do more payload. It's not easy as this, because you can't simply put in like more like 40 kilograms mass or so, and say, okay, I have less fuel reserve. So we really need to have these fuel reserves to do maneuvers. And one thing that I don't think I've pointed that out correctly, we want to launch with a so-called satellite carrier. Not with a carrier where you could shoot up your house in the sky. We want to launch with a really small carrier, so that is normally being used to shoot satellites into the orbit. So we really have to build a very small lander, a very small rover, and everything else. So it has to be really compact. And just want to make one thing, because there's 1 minute on the clock. And we will be, I think, right out there after the presentation with a lot more prototypes. Other side, okay, sorry. Right over there. No. And so you can ask us all the questions you want after the presentation too.
Yeah, and we will be at the workshop where you can ask other questions and touch the rover and do fun stuff with them.
Okay.
So, give a big applause.